Good morning, everyone. I'm Rosa de Finis from Polytechnic University of Bari, and I'm going to discuss the work Consideration on Thermoelastic Effect in Proximity of Crack Tips on Titanium and Aluminium, a new formulation that is focused on presenting a new thermoelastic formulation that accounts for the mean stress dependence to properly investigate the stress distribution in the proximity of the crack tips of high diffusivity materials. Moreover, in this work, the implication of using the new formulation and classical theory in assessing stress intensity factor will be presented. The experimental data will confirm the validity of the new formulation, but firstly, let me to show you the outline of the work that involved a brief description of the state-of-the-art on the use of capability of TSA in assessing the stress intensity factor and the crack tip position. Secondly, the aims of the work will be clarified and the theory will be explained. The new formulation will be presented after the theory being introduced, and after I will present method and data analysis, providing the workflow of the analysis and the adopted approach for extracting from temperature data the thermoelastic temperature variation. And finally, the experimental setup will be also presented, and the results will demonstrate the consistency of the theory. Stress intensity factor is used for describing the stress state and then the mechanical behavior of the material in presence of cracks, and it can be experimentally assessed using contactless technique such as the thermoelastic stress analysis technique. Stanley presented, for example, a procedure based on Westeergard equation for the elastic plane stress condition. In this case, the stress intensity factor can be obtained by relating the first stress invariant and the crack tip position, and the main advantage is that only a series of signal profiles, in this case horizontal signal profiles scanning around the crack tip stress field and away from the plastic zone, are required to obtain the stress intensity factor measurement. The main drawback of the approach refers to the neglection of the T-stress term in the Westeergard equation that led to an error in SIF evaluation. And on the other side, instead of using a linear interpolation method, the over-deterministic less square fitting method can be obtained for a more accurate estimation of the stress intensity factor. In this case, by using a Williams series expansion. In this work, the approach has been used for assessing the effective stress intensity factor from thermoelastic map. Even in the work of Pitaresi et al., an over-deterministic less square fitting method using the Williams series expansion is adopted. In this case, T-stress was considered in the analysis, and the stress intensity factor was determined as a function also of the number of terms in the Williams series function, and also the extent and position of the area for data input were also assessed in this work. All these work are based on the classical theory of TSA, in which temperature change are related with the stress change through the thermoelastic constant for an isotropic material under linear elastic and local adiabatic condition. But this classic approach is only valid if the change in the mechanical properties of the material with temperature can be considered as negligible. Moreover, depending on the material, the problem of the mean stress influence was also not addressed. That's why we're dealing with this issue, the issue of considering the second order effect in the thermoelastic signal formulation. And in fact, in this, the aim of the present work is to show a new formulation that includes the mean stress dependence to investigate the thermoelastic effect in the proximity of crack tips for titanium, and also to show the differences in SIF evaluation with and without taking into account the mean stress dependence in thermoelastic formulation. Thermoelastic effect relates the temperature change with the change in the sum of principal stress for an isotropic material under linear elastic and adiabatic condition. The thermoelastic equation was derived by imposing the conservative laws which govern the mechanics of small quasi-static deformation and the second law of thermodynamics. And we can see that the time derivative of the temperature, in fact, in function of the first stress invariant and the principal stress, and by also considering one-dimensional stress state where the stress changes over time with a sinusoidal waveform, we can see that there is a mean stress dependence that arises when the material mechanical properties such as Young modulus depends on temperature, and it is also interesting to observe another terms running at twice the mechanical frequency. By considering the previous formulation and taking into account the material constant, the principal stress, and by considering that the principal stress under generical sinusoidal loading can be written in function of its amplitude and loading ratio, it is possible to obtain this wide expression for time derivative temperature variation, thermoelastic temperature variation in function of the material constant A and B, Poisson ratio, and the amplitude of the principal stress in direction 1 and in the two directions. And this equation in a more compacted forms represent the general expression of the thermoelastic signal in proximity of the crack under the hypothesis that this small temperature, are very small, very small if compared to the environmental temperature. In present work, we will focus on this term that represents the amplitude of the thermoelastic signal in order to investigate the effect of the mean stress and also to understand how the second order terms change the thermoelastic equation in proximity of the crack in the new formulation. So, by considering the Westeergard solution, where we consider the T stress, the presence of T stress, this term, and by coupling this equation in the general expression of the thermoelastic signal as previously seen, we can see the new formulation if we consider that the B constant is different from 0, and in case we have B equal to 0, we have the classical solution used for relating the thermoelastic signal and stress intensity factor. And this one is the new formulation where we can see that the temperature variation depends also on the stress ratio and the material constant B and the Poisson ratio. In this case, here we have the Williams solution, series expansion truncated to the third term that is combined with the TSA second order equation to obtain the new formulation. The thermoelastic temperature variation clearly, even in this case, depends on the stress ratio and depend also on the Poisson ratio and the B term that is different from 0. And we have also the classical solution for relating the thermoelastic signal without considering the mean stress effect. Here, this quantitative, this temperature from classical solution and this order from new formulation are being used to obtain the synthetic, corrected and non-corrected thermoelastic temperature variation that will be compared with measured thermoelastic data. In this slide, we can see the temperature variation that can be obtained by using a signal reconstruction algorithm based on least square method to extract from temperature the thermoelastic signal. We can see in this slide also the other quantity that can be used, in this case this and this other one, that can be used to study under the point of view of a reversible process the phenomena associated with fatigue crack. But in this case we will focus on this term and this term that is related to the thermoelastic temperature variation. This slide represents the workflow of the procedure. In this case, after the experimental test and lock-in analysis that decompose the signal into the thermoelastic phase shift that allows to obtain the crack tip position initial value and the elastic stress field boundaries, and the thermoelastic maps that are included in the implementation of the over-deterministic last square fitting methods. In particular, an over-deterministic set of equation is written according to the material constant, the corrected and non-corrected, that is according to the thermoelastic temperature variation with and without mean stress effect according Williams and according Westeergard, and imposing loading condition. The over-deterministic methods led to obtain the best fitting parameters that are the stress intensity factor for Westeergard and the three coefficients considered, the stress intensity factor, T stress, and constant A for Williams, and also it led to obtain the crack tip position. The test material was a titanium grade 2 small scale compact tension sample tested at MTS loading frame with a 25 kilonewton of capacity. The loading condition involved a stress ratio of 0.1 and 0.5. The thermal acquisitions were carried out by using a FLIR X6581 infrared camera that acquired 1500 frames at 200 Hz. In order to assess the thermoelastic constant, a calibration was carried out. The calibration involved the following steps. Firstly, the acquisition with infrared camera of the thermoelastic signal during a sinusoidal loading test on dog bone samples at different levels of mean load. Secondly, the lock-in analysis and calculation of the first harmonic amplitude and reference temperature T0, and finally evaluation of the thermoelastic parameters A and B by just fitting, we can see this, by just fitting the experimental data, and we can see the value of this material constant here reported. In this slide, we can see the isopachic curves for experimental data and the curves of synthetic data obtained by the new formulation and the classic formulation that are red dotted contours. We can see that for each stress-strain ratio, 0.1, 0.5, a great agreement of the black solid contour that represent the new formulation temperature variation assessed by using Westeergard with the experimental data, and the same consideration can be drawn also for the stress ratio of 0.5. Even in this case, referring to this opaque of experimental data and synthetic data obtained by using the Williams series expansion, we can see that the new formulation that is represented by black solid contour that take into account the mean stress effect approximate very well the experimental data, and the same consideration can be also drawn for the 0.5 stress ratio. In order to make more consistent consideration, in the following graph we can see the stress intensity factor assessed by using Westeergard solution and the new formulation, and a Westeergard solution for the classic formulation, and compared for both stress ratio to the stress intensity factor evaluated according to the standard. We can see that there is a great agreement with the data from new formulation and those provided by the standard with respect to the stress intensity factor assessed by classical theory do not accounting for the mean stress effect. The same results can be obtained for each stress ratio when we can see that the stress intensity factor evaluated with the new formulation are of great agreement with the stress intensity factor provided by the standard. In this case, the data from non-corrected theory, where the mean stress effect was not accounted for, are very scattered with respect to those order obtained by using Westeergard. Finally, in this presentation, we provide a new formulation. We propose a new formulation to account for the mean stress effect in proximity of the crack tip on materials of titanium, such as titanium and aluminium. The proposed equation can be a useful tool to understand the limit of applicability of classic theory and well-known solution and the error made in neglecting the second order effect. Thank you for your attention.